So we started talking in our last lecture about radiometry. Now we've covered the very basics of geometry already. What's the geometry of the scene? What's the geometry of the camera? How can we use these two to understand the 3D world from two-dimensional pictures? But the same is true for light, right? Radiometry, the study of light, actually tells you how you can interpret or how can you understand the intensity or the radiance in your pixels given the, how can you understand the three-dimensional world information given the radiance in your pixels, right? Okay. Now we talk about foreshortening. So remember, foreshortening means that if I have an object, right, I have my hemisphere here, and I have a light source, right? I'll call this a light source, say the sun, and the sun reaches a specific point given a specific solid angle in that hemisphere, right? And that also, that of course defines the foreshortening. That means the amount of foreshortening that I have from my point of view of my light source, right? So if I have the light source right here on top of me, it is not foreshortened, but if it foreshortens a little because it's at a solid angle, then I lose some amount of that power coming into me. So we define that solid angle, the differential of W, as the differential of the area. Remember that little area here, the differential area on my hemisphere, times the cosine of theta n. Theta n is, of course, the angle that defines the normal vector of that small differential of a plane, the dA, right? And we normalize this by the radius of the hemisphere. Excuse me. Generally, the radius of the hemisphere is going to be 1, and therefore this just cancels, right? It can delete that. So with that, we define radiance. And remember, radiance is the power again is the amount of energy per unit time that travels at some point in a specified direction per unit area perpendicular to the direction of travel per unit solid angle. Okay, so again, the power, how much of the original energy that comes out from the source that reaches me, right, given that direction of travel, which of course, let's say that I define my radiance as L, capital L, arriving at the point capital P, a world point, given some angles in that hemisphere, right? Remember what we had drawn. We had drawn a hemisphere on a surface that looks something like this, right? And we had our hemisphere here. Right? We had something like this. And then if we had our point P here and our vector, we had defined this angle right here as phi, and this one right here as theta, right? And note that we're going to normalize this per unit area, right? Perpendicular, this is that area right here that is perpendicular to the direction of travel per unit solid angle, okay? All right, that's where we were. We also said that radiance is constant along a straight line. So if I move about one direction, right, one axis, then the radiance doesn't change, right? About that, that's obviously not true because some of the power dissipates for a variety of reasons, but to a good approximation for what we need, it's good. If a radiance of a patch, let's call it a patch at point P1, okay? If I have the radiance of that patch defined, a small patch defined by a point P1, then the energy transmitted by the patch into the region of the solid angle dW in that direction, theta phi, it's going to be this times the cosine of the angle for that point times the differential of the area of that point, 1, times now the solid, so this times the solid angle that I have, and what else did I say? And because power is defined by unit time times differential of time, okay? Now note that I'm separating the idea, the radiance, separating the idea of the amount of power that reaches a point from the idea of a source, okay? This up here is a source. And sources are going to be treated differently because we are going to assume, and again, this is an assumption we need to do to make the equations workable for us. We're going to assume that surfaces in our world do not generate energy. Only sources can generate energy, okay? Now, obviously, that's not true. Your body is generating energy right now, right? That's why you consume calories, right? Thank goodness. So we can eat more chocolate. So, true, but most surfaces, like this one right here, does not generate energy, right? So we're just going to assume that in general, surfaces do not generate energy. We're also going to assume that the radiance, so radiance, note that it can either define the incoming radiance like this one that I have defined here, right? This is the incoming radiance, but, so let me call it maybe incoming, right? The incoming radiance, but I also have the outgoing radiance, right? Because when that source sends this light ray onto the point P, then once it reaches that point P, it gets scattered in all possible directions, right? Into the world, and that is going to be given by the outgoing radiance, okay? Yep. Now, we're going to assume that the radiance leaving a point on a surface is due only to the radiance arriving at that point. Okay, so for each of these directions, the radiance living in any possible direction has to be given by the incoming radiance, period, at that point P. Okay? Now, again, that is not true. That is not true probably for that board, although this is pretty shiny, but certainly not true for this. And it's certainly not true for your skin or your body. And the reason for that is that when I send power, light is nothing else than power, right? When I send power onto an object, that object absorbs part of that power, right? So if you put a light, you focus a light onto a table, even a wooden table, it will get warmer, right? Why does it get warm? Well, because it's absorbing some of the energy that you're sending into it, right? We're going to ignore that. We're going to say that it does not absorb any energy, that all the incoming energy or the incoming power leaves that point and at that point, right? Now, what also happens is that some of that internal energy that gets into that object, so let's say that I have incoming power here and that object absorbs some of that power. Now, I could say that after a while, maybe because this is getting hotter, it's actually emitting power back out from that point. But that's not exactly what happens. What's going on is that if this is my surface here, and I have some incoming energy at that point P, then this gets absorbed, right? Or a portion of that gets absorbed. And because of the molecules in that surface, it starts to bounce back and forth. And at some point, it may actually leave that surface, right? And the problem is that it leaves at a different point that it enters, right? And that's especially true for your body. Your body has multiple layers of skin and fat and muscle. And the light that comes in gets inside your body in one direction. It bounces throughout your cells at the body, and then some of it will just shoot out from another, out in another direction from another point, right? That makes it extremely difficult to model. That's why when you look at computer graphics, even to this day, they can model a lot of surfaces really well. But human skin, it's tough, right? You can never find a real good computer graphics model of a skin of a person that looks realistic. And the reason is this, that simulating this coming in of the energy, bouncing back and forth within the skin and cells in your body, and then exiting at some other point is extremely complicated, right? So we're going to ignore all these details. We are just going to assume that the incoming and rather than the outgoing radiance is only due to the incoming radiance. We're also going to assume that the light leaving a surface at a given wavelength is due to light arriving at that specific wavelength. Now, remember, wavelength specifies the color, right? Okay. Now, color doesn't exist in the real world. We only have different types of frequencies, right? And depending on the wavelength, then I have one color or another, right? So we're going to talk more about this when we discuss color. But if an object is black, is that black? Well, close, right? It's bluish. This is black, right? If this top here you probably don't see. Okay, how about this? This is red, okay? In fact, this is incorrect for me to say red. We say it's red because we see red, right? But what this means is this object is anything but red. Okay, so this object absorbs, remember the absorption, absorbs all the wavelength except the one that we associate to redness. So the only one that leaves that object is the wavelength of red, or what our brain associates to red. So we call it red, but that's actually misleading because it's anything but red. So let's say that I want to paint this wall red. Which colors can I use to make that wall red? Which colors of paint can I use to paint a wall red? Red. Any other option? That's it, right? No, but seriously, people think that you can combine different colors to get to red. And it's impossible because to generate red, you have to have an object that absorbs every wavelength but red. So you have to have that object. You cannot have object for blue, yellow, and what have you, and combine them, and then all of a sudden, it doesn't absorb red. No, if you have yellow, it means that it does absorb red, right? That's why it's yellow. So it doesn't matter that you add blue to yellow, it will still absorb red, right? Now, this is different from when you have light sources. When I have a light source that is yellow and a light source that is blue, and I combine this, that's different because now I'm adding frequencies, right? That's a completely different process. So now I can generate multiple colors with just basic components. That's why your monitors, your TV, your computer monitors are RGB. They only have R, G, and B. You can only generate red, green, and blue. But because I can generate these three by combining these frequencies, I can generate millions of colors. Absolutely, I mean, literally millions, right? But that cannot be done with paint. Paint can only be the color that the paint is originally. You can never combine any other colors with it to make it look the color you want, right? There are two different processes. One is absorption, the other one is generation. And when you generate, you sum over the frequencies that you are producing, right? The amplitudes and frequencies. Okay. Now, for this, to make this distinction, let's talk about irradiance. Irradiance is the incident power per unit area not foreshortened. So that means that I'm going to take the radiance, right, the incoming radiance at point P with a certain direction. So let's call it theta I, phi I. And remember, I need to multiply it by the direction and normalize it. So multiply by the cosine of the incoming angle times dA times dW. And I need now to normalize this by the differential of the area. Okay. So that means that I can cancel these two terms, and I'm going to just write that this is the incoming radiance times the cosine, which is the foreshortening, right, and the solid angle, right? Okay. All right. BRDF. This stands for bidirectional reflectance distribution function. The bidirectional reflectance distribution function is the ratio of the radiance in the outgoing direction to the incidence irradiance. Okay, so the ratio of the radiance in the outgoing direction to the incident irradiance. Let me write it as rho of BD, I'm going to say, for the bidirectional reflectance of, now I'm going to use 4 angles, theta O and phi O correspond to the direction of the outgoing direction, and theta I, phi I for the incoming direction. And what did I say this is? This is the ratio of the outgoing, which is LO of P for these angles, over the incoming irradiance, which is LIP phi I, theta I phi I, times what else? The cosine of phi I, which is a foreshortening, times the solid angle. Right. So let's think about what the BRDF defines. The BRDF is specifically defined for a point on an object, okay? A 3-dimensional world point. Now, it tells me that if I have a certain amount of irradiance, that means given a specific foreshortening, right, and a specific power of my source that's illuminating that point, right, per solid angle, right, it's a normalizing factor, how much of this is going to go out, right? It's going to refract back into the world in a specific direction. Okay? So incoming in this direction and outgoing in another direction. Okay? So now, if I want to compute, let's see if you can give me the answer to that. If I want to compute the radiance leaving a point in a specific direction, right? This has to be equal to, it's not a tricky question. I know I keep saying this, but it's not. If I want to compute the outgoing radiance at this specific direction, this is going to be equal to what? The BRDF times the irradiance. Very good, right? The BRDF of my object, rho, what do you call it? BD of the outgoing times Li of P phi I and theta I phi I. times the cosine of the foreshortening and the solid angle. Now, here I have a hemisphere, right? Let's call it omega. I have a hemisphere, right? This is, I take a three-dimensional sphere, S2, right? And I cut it in half, okay? So, if I now want to compute this for every possible incoming irradiance, right? Because I have to consider every possible incoming. Then I need to do what here? Integrate over my hemisphere, right? Correct? And the differential of the solid angle indicates every possible direction, correct? You can also write this as integrating from 0 to 2 pi, right? This is going about the circle of the hemisphere. And now I'm going to go in that other direction of the hemisphere from 0 to pi halves, right? And now I have Li of P for theta I, phi I. The cosine of theta I. Now I need to multiply it also by the sine of phi I to represent both of these and the two differentials. Okay. Now, let's do some simplifications, shall we? Because, as always, this is just too complicated. I mean, can we work with these equations? Sure we can, right? But this is image processing 101. So let's try to simplify it a little bit. So radiosity, let me define another term, radiosity. We're going to use radiosity as we use radiance here, but in the particular case that the radiance leaving a point is invariant to the outgoing direction. Okay? So the radiance leaving a point P is independent of exit or outgoing direction or outgoing angle. You can also then define radiance as the total power leaving a point on a surface per unit area on that surface. Same thing. And formally, we can write it, say, B for radiosity of a point P as the outgoing radiance for times the foreshortening, of course, for every possible solid angle, and now I integrate over my hemisphere, right? Okay, if the surface has constant radiance, then I can write BP is equal to LOP because it's constant, right? If this is constant, then I can write this times, I'm going to integrate over the hemisphere like I did there, from 0 to pi halves and from 0 to 2 pi, the cosine of theta and the sine of phi. And what is this equal to? This is equal to pi, right? So I can write that this is pi LOP. With that result, I can now simplify the BRDF for something that's called the directional hemispheric reflectance. Let's do that. Directional hemispheric reflectance function, and this is given by the radiosity rather than the radiance. So the BRDF, it's a quantity that is given by the variabilities for the incoming and outgoing direction, but the directional hemispheric reflectance function is not. The light leaving the surface is going to be assumed to be independent of exit angle, okay? And I'm going to say rho in that case of dH for directional hemispheric. For an incoming direction is equal to, let's see, I have my outgoing radiance at point P for every possible angle, outgoing angle that is, times the foreshortening times the solid angle. And remember, because it is independent of the exit, or because I want to compute the radiosity, I integrate over the hemisphere, and I still have to normalize this for the irradiance, so I have P of theta I phi I, and cosine now of phi I dW. And you can say dWo and I because we want to distinguish them. Okay? And note that I could have just written this as integrating over my hemisphere the BRDF that I had before, BD, for each specific incoming and outgoing angles, right? I could have said this as well, but I'm going to stick with this. All right, final simplification. Albedo. That's the one we're really going to work with. Now, I have computed the DHR, which is invariant to the outgoing angle, right? Now I can make this invariant to what else? Anyone? The incoming, thank you. To the incoming angle. And in that case, I talk about the albedo. I'm going to call this rho d. And in that case, this is going to be equal to integrating over my hemisphere some constant, rho, times the cosine of the foreshortening times the solid angle. And this, we already know, this is equal to pi. So this is going to be some constant over pi. Okay? So in general, we're going to say that, in our case, in general, we're going to say that the BRDF of our function is given by the albedo, right, over pi, or I'm just going to call it rho over pi. Okay? Or the other way to say this is that the BRDF is given by, that the albedo is given by pi times the BRDF, right? Because I'm assuming that it's constant in every incoming and outgoing direction of my hemisphere. Final assumption. I'm going to assume that surfaces are what's called Lambertian. And we're going to discuss this in detail next. But let's think about non-Lambertian surfaces first. You see this surface right here, this whiteboard? It's pretty shiny, right? Do you see these specular reflections, these directions of the source that are refracted back in specific directions? It gives you this directionality of the light source. This is non-Lambertian because the outgoing direction, or the radiance of the specific outgoing directions, is different than from other outgoing directions, right? Obviously. But for many other surfaces, it doesn't matter how you illuminate. For example, cotton, it doesn't matter how you illuminate it. It seems that it's constant, right? It doesn't matter which outgoing direction you're looking at. It's just pretty constant, right? This is called Lambertian. It means that it's invariant to that. And that's what we are going to try to model to define our shading model. So let's see this. Let's see how we can use all this to define models that are useful to us. Now remember that when we were working with geometry, we use all the geometric information that we had about the world and the camera to define models, camera models. Now we're going to do the same thing. These are called shading models because they define the shading that you observe in the image. Okay? Now remember that the shading is given by the luminance. Remember the luminance? The amount of power that is given at each pixel. So we'll call these shading models. And there are two ways in which a surface can change its luminance or its shading. One is the albedo. Depending on the albedo rho that I have, it will refract more or less or different amounts of radiance, right? And the other one is the light source, right? Okay, let's see how this works. To talk about this, we're going to talk about Lambertian surfaces again. Which again means nothing else than that the brightness or the luminance at each individual point on that surface is uniquely determined, right? They're all one and the same. Okay. So to see this, let me consider this case. Let me consider a very simple case. Going to consider a two-dimensional plane like this one right here, right? And I'm looking at this maybe like that. So that's my two-dimensional plane in 3D. So I may have something like this. Dimensional plane. And I'm going to do something else. I'm going to insert a wall in that plane. And that plane, you can consider that it goes to infinity, right? In every possible direction. So it goes to infinity in this direction. It goes to infinity in that direction. And same thing here, right? And we can say the same thing about this wall. It's infinitely long in every possible direction, right? You see how this works? So I have an infinite plane here and another one which is orthogonal to it. Now, what happens if I illuminate this plane, this first plane here, with a light source at the top, the very top, which illuminates this with equal illumination, right? Equal intensity, equal power at every possible point. Okay. What happens? I don't know. Let's see. Let's consider 3 points. So consider point A here. Well, this point A, this first point. I'll consider another point B, maybe here. And another point C, maybe here, I don't know, here. Okay. Actually, why don't I do this? Let me put it here. Okay. Now, how am I going to analyze this? Well, what I can do, I can have a hemisphere as I had before, right? In each of these points. And now I'm going to see what this hemisphere sees in this environment, right? So let me draw this from, so if I'm looking at this hemisphere from the top, I only see a circle, right? Let me draw this circle here. And that circle corresponds to that point C, right? I'm going to have another circle for A. And another circle for B. Right? This is looking at the hemisphere from the very top, so I only see it as a circle. Okay? Now, let's go to A, this one right here. all the points are equally light, have equal lightening or light, okay, light source. This is weird. All right, equal power of the light source in each point. So if I have this point here at the center C, right? How much light does it reach through that direction? This one right here, specified by this hemisphere. Maximum, let's call it P, I don't know, power P, okay? How about this one? Same. How about this one? How about this one right here? And think about this. There's a wall here that's infinitely tall. This is going to prevent any of these incoming angles from having a direct observation of the light source, correct? So I'm going to have something of that nature where this half of the hemisphere does not see the light source and this one does, correct? Yep. How about for B? For B, I'm going to have the exact same thing. Half of the hemisphere is not going to see the light source, and half is. And how about for C? Same thing, right? Half is not going to see the light source, but the other half is. Correct? Okay. Wonderful. Now, let's say that I change my environment as follows. I'm going to change this like that. I'm going to still have an infinitely tall wall, but now this wall stops right here at that point, okay, which is aligned with C. And maybe I can do this better. Okay. And this is obviously going to continue, right? Oops, actually. This way, right? Now, in that second case, what is going to happen to my hemispheres? Let's see. This one for B, this one for A, and this one for C. Now, how about A? What's going to happen to A? Is A going to be any different? No, of course not, right? There's no difference in A. A is still going to be the same, right? Because that half of the hemisphere cannot see the light source because of the wall. But how about C? C now has this quarter of the hemisphere that doesn't see the light source, but 3/4 do, right? So C is going to be something like this, correct? And how about B? B, it's probably going to be about the same, right? Not exactly the same, because there's going to be maybe something like this. Right? Because there is this direction, right? that is going to have a small effect here, right? Yep, see that? So what that means to us, this means something really cool, that the incoming radiance that I have specifies the structure of the scene, which means, as in geometry, that I can recover the three-dimensional structure of my scene from knowing the radiosity or the radiance that I observe of my world. That's what we're going to do in shading models, right? Okay. Let's get to it. To do that, we're going to use something that's called point sources. A point source is exactly what you think it is. It's a source that is defined by a single point. Okay? Now, point sources cannot model light like this fluorescence, right? Because these are long tubes. They're not a point, right? And they can model many other types of sources that are small in area, or that they may be very large. Maybe think about the sun, right? Huge, but they're so far away from us that the size of the source compared to the distance from the source to us, it's so small that we can consider it a point source, right? So in fact, most people consider the sun a point source. Now it sounds ridiculous. The sun is huge. But again, the ratio of the size of the radius of the sun over the distance from the sun to Earth, it's just so large, it really doesn't have much of an effect, right? Okay. So because of that, if I consider light sources, when I have a surface here, say a surface like this, and I have a source that has an area, theoretically, but that area, or that volume rather, is compared to the distance, oops, oh yeah, I do use R, okay, compared to that distance, that area or diameter, say, is much, much smaller than my distance to the surface. Okay. Now remember again that what I'm doing really is for a light source here and a point here, I'm using a hemisphere, right, like this, and I am projecting this source onto that solid angle, right? That's defined by that, or that little area. Let me call it maybe epsilon. The little area, which is the image, right? The projection, the projection of that object on top of the hemisphere, right? That projection, right? So that's going to be really tiny, right? If it's a point source, it's going to be a differential of an area, right? Okay. So let's see how we can derive now our shading model based on this idea. What do we need? We need the radiosity, right? Okay, let's see if someone can help me derive the radiosity of this light source here. Now let's say that this light source, the amount of power that the light source emits, it's called the exitance, okay? So we'll give it a value of E. This is the exitance of the light source. Okay? That's the irradiance, basically, that I'm going to receive from that light source, right? Because I'm assuming that there's no loss in power between the light source and myself, right? I know, it's absurd, but we're going to assume that. So what would be the exitance? So here I can compute that a small region that I have here, the solid angle, that is substant on the hemisphere as this area epsilon over that distance that is called r squared, right? That's my solid angle times, what am I missing? The foreshortening, right? Times the cosine of the angle of the foreshortened angle. So now the radiosity is going to be E times this, right? Times, what am I missing to compute the radiosity? Something about this point P here. What am I missing? The BRDF, very good, which is equal to rho over pi. Now, because I'm computing the radiosity, I integrate over the whole hemisphere, right? This is going to be multiplied by pi. So these two cancel out. And that is the equation of the radiosity at that point, okay, for a Lambertian surface. So far, so good? All right, excellent. Now, let's look at this again from a cross-section. This one from a cross-section. I have my surface here, right? This is my surface. I have my light source, my point light source that reaches a point capital P here. And that capital P, right, as we have done before, the point P is defined by its normal, right? The normal defines the shape of the object, right? Remember that? So let's call this capital N of my point P. That's the normal of that point. What's that angle right here? That's a foreshortened angle, right? Theta. Now, what do I know about the normal of a point? Anyone? What do I know about the normal? That it has norm 1. Good. Now, the radiosity is equal to this thing here, okay? And I have to make this equal to these two vectors. So let me call, so this is the source, right? So let me call this other vector S of P, okay, for source, right? Now, I can get, if I do, how about this? I do NP inner product with SP. That is going to give me the cosine of that angle, right? And what am I missing? I'm missing the norm of SP, right? Which has to be equal to this thing right here, right? Correct? So the norm of SP has to be equal to, I'm going to assume R equal to 1 for simplicity, epsilon squared E, okay? If you don't want to assume R equal to 1, then you can just write this into here, it's up to you, as R at point P squared. All right, and now what else do I need? The albedo at time P, right? So this is equal to this. Famous equation right here that we have derived. It's known as the standard model of a point source. Okay. We have three components in this equation. We have the albedo that determines the amount of energy that is bouncing back and in which direction, right, of the object. We have NP, which defines the shape of the object. That's a three-dimensional shape of my object. And I have SP, which is the information of the source, the light source, right? The direction and intensity of the light source. Now, if I know one of them, I can compute the other two. Linear least squares. All right, just so some question faces. All right. In general, this distance for a point source can be considered to be large, right? The sun, it's the obvious example. Which means that this term here, right, is then constant. Okay? That's what it means. Because obviously the normal doesn't change. The normal defines the shape of the object, right? That's not going to change. What the R can change is the vector of the source, right? The intensity. But you know, if I have a curved surface like this, and I have a source right here, then obviously every point is irradiated differently, right? But if my light source is here, then this one or any other vector are pretty much the same vector, right? So if I have Earth and the sun, you know, far away, then the Earth pretty much looks like a point compared to the sun and its distance, right? So every point on Earth is basically illuminated the same way with respect or from the point of view of the sun. So this is a pretty good assumption that we can make, in which case we can probably write NP, right? The radiosity is NP times SP maybe divided by some R constant, let's call it RO square, right? Which we can then simplify as NP times S, because S is equal to SP times or over RO square, right? It's a constant now. And then I'm missing the albedo here, so I have that the radiosity BP is the albedo at that point times NP times S, okay? And this equation is the one we're going to work with. All right, any questions? Okay, so let's see how we can design an algorithm to get to solve for the unknowns, for the two unknowns that we're going to have. This is going to be called photometric stereo. It's called photometric stereo because, like in geometry, that we use stereo vision, but with radiance instead of the geometrical relationship between the camera model and the three-dimensional world. Okay. Now, obviously, the radiosity that we have derived here is with respect to one light source, right? So either we have just one light source in our scene, or we are in trouble because then we have more than one of these vectors. If you have more than one, then things become very complicated. There is a way to extend this by simply saying that the radiosity that I observe, so I make an assumption that the radiosity that I observe, that's BP, it's nothing else than the sum of all the BPs for, say, B sub S, where S is the source, for all the sources that I have, right? Now, this is obviously a gross simplification of what happens in the real world, but we can simplify it like this if we have more than one light source. And that means that our algorithm is still applicable to cases where we have more than one light source, right? Okay? All right, in this case, this equation will be given by BP is equal to the sum over all sources of rho P times NP times S. Now, in practice, you need to modify this for a very simple reason. Even under this assumption, there is a problem with this equation. This equation assumes that what? Anyone can tell me what the underlying assumption of this equation is? Yeah, well, that's what I said. You're right, sort of right. But that's not what I'm looking for. But that's what I said at the beginning, right? That's a gross simplification of how light sources interact. But there is one thing that I cannot avoid, that I cannot ignore. There's one thing I can never ignore, even in this equation, which is incorrect as stated. It assumes that every point does what? Sees what? What's that? Every point sees every single light source, right? And that may not be the case, and in that case, we need to solve for that problem, right? And that's what we'll do in photometric stereo. We have to know which points see which light sources, because obviously that may not be the case, right? If I have light source over there, another one over here, and I have an object here in the middle, then this point sees this light source, and that point sees that light source, and this point right here, right, sees both. But we have to know which sees what, right? So we need to solve for that particular problem right there. All right, but if we can solve for this particular problem, then again we can use this model. If we know one of them, say that I know the vector S, right? I know where my light source or sources are. Then I can solve for NP and rho. Okay? That means the albedo and the shape. So I can recover the albedo and the shape, much like we recover the structure and the motion of the cameras in the structure from motion. Here I can recover the shape, meaning the structure again, and the albedo from a certain number of observations. Okay? And this is called shape from shading. And now, again, this is to be compared to structure from motion, right? They're one and the same in essence. In the structure from motion, what I need to recover is the shape of the object and the movement of the camera or the movement of the object with respect to the camera. Here, the camera is going to be fixed. It's not going to move. But I can still recover the shape and the albedo that determines the shading of that object, right? Because obviously the albedo of that surface versus this surface here versus another surface here, they have different albedos. That's why they have different shadings. Okay? So that's what I need to do. And how am I going to do that? Well, I'm going to use different sources. And every time I use a different source, I'm going to obtain a number of equations. And then I'm going to put my equations together. And I'm going to use, what's the name again? Linear least squares, right? To solve for my system of equations. And that's going to give me these two unknowns. Okay? All right, we'll see how to do that. It's, remember, this is called photometric stereo. And we'll derive the exact algorithm next time. I'll see you then.